So the orbits were specified with a number, 1, 2, 3, 4, 5, etc. Orbitals are also specified with a number, but also with a letter. The number is called the principal quantum number. It's given the symbol n, and that specifies the principal shell of the orbital. So as n gets larger, the energy increases. So the principal shell 3 is higher in energy than shell 2. So if you think about the ladder, if you fall from the third rung or you fall from the first rung, there's a lot more energy involved in falling from a higher level. The letter gives us a subshell or a sublevel, and that gives us the shape. So the possible letters are S, P, D, and F. And there is a historical reason why they're not A, B, C, D. But there they are, S, P, D, and F. So in the first principal shell, there is one orbital. It's an S orbital, and the S orbital is spherical. So this is a dot representation of that orbital, like a multiple exposure photograph, where you would take a picture of the electron, and you'd get this overall picture that most of the time it's in there. It's three-dimensional, and so the higher the density of the dots, the more likely you are to find the electron there. We can also represent it as a geometric shape. So it's a sphere, a ball. This is not a fixed container that contains the electrons. It's just easier to draw than a whole bunch of dots all the time. So this represents a volume within which the electron would be found 90% of the time. We fully expect that the electron will be outside of this 10% of the time, because they're small and unpredictable. It's a little bit like my son Andrew. He's gotten a lot better. He's 8 now. But when he was like 2 and 3 years old, you just never knew, He should be in the house, right? 2, 3-year-old children should not be wandering around the neighborhood. But he could get out of almost anything. And so one time he took off barefoot, stole the neighbor's big wheel, and drove 3 blocks to my brother-in-law's house. Right? Unpredictable. He's supposed to be in the house or in the yard, right? Most of the time, like centered around the television, right? But sometimes, not so much. Or you'd find him out on the corner, or the neighbor would bring him back from the middle of the street. Little guy, he's still alive. I didn't kill him. Don't call anybody on me. But electrons remind me of Andrew, right? Small, squirrely children, and you just never know. It's like, well, probably it's within this region, but he's supposed to be at school, but is he? We can't guarantee that. So that's what they're like. So this would be overlapping the two, the dot representation and the geometric shape, and we see that some of these dots are outside of the sphere. So that's what we're looking at. So in a hydrogen atom, there's one electron. And if that is not disturbed, we're not zapping with energy of some sort, that one electron is going to be in the lowest energy place it can be. It's going to be within that first energy level, the 1s orbital. That's called the ground state, the lowest energy state. Electrons generally are going to seek out the lowest energy state available. This reminds me of teenage boys. So some of you may be teenage boys, don't take offense. I have teenage boys in my house. So they sleep a lot. They'll get up, they'll go to football practice, they'll do things, high energy, and then they come back and they just flat. Maybe texting, but they're in bed, they're horizontal or on the couch, right? Low energy. So they'll eat food, they'll get up, they'll do stuff, and then they're out of energy, right? That's what the electrons are doing. They will go to higher energy levels, but they're not going to stay up there. They'll come back to their ground state, the lowest energy level. So the electron can absorb energy and jump up to a higher level. That's called an excited state. It's unstable. It's not going to stay that way. All atoms have one ground state and many different excited states. But the excited states are not stable. And so we generally don't really even talk about the excited states because there's so many of them, it doesn't really matter. We're interested in the ground state, what they're going to come back to. So principal shell 1 has one subshell, that S subshell. Principal shell 2 has two subshells. It has an S subshell and a P subshell. So the S subshell, again, is spherical. It's just bigger than the one in the first shell. So it's larger, slightly larger, and it's also higher in energy. And then the P subshell has 3 different orbitals within it. And they all have the same energy and the same shape, but they're oriented differently in space. So there's the dot representation and the geometric representation. One's aligned along an x-axis, one along the y-axis, one along the z-axis. They're perpendicular to each other. So the number of sublevels is equal to the number of the shell. So the first shell has 1 sublevel, the second has 2, the third has 3, the fourth has 4. So they all have an S subshell, and the next one would be P and D and F. And this is all just not going to make a whole lot of sense to you. Yes?
Do we need to distinguish the shape of each subshell, or just know that there are different?
That's a good question. Do you need to know the shapes? You should know the shape of the P subshells. So it's this dumbbell shape. Kind of looks like 2 balloons to me. And the S is a sphere. Those are the 2 you need to know. The others are kind of crazy, and I'm not going to expect that. So the third shell has 3 subshells, S, P, and D. And again, the 3S and the 3P, same shape, because the letter tells us the shape. Same shape, but they're larger and they're higher in energy. And then the D subshell has 5 orbitals, and that's what they look like. What? That's crazy. I will not make you draw those. You do not need to remember them. But there they are. They're weird. Okay? So we have a shorthand for representing what subshells the electrons are in. So we call it an electron configuration. Shows us which different orbitals have electrons. So for hydrogen, here's the element symbol. Hydrogen has 1 electron, and so that electron in the ground state is going to be in the first principal level in the S subshell, and we write a number 1 here to indicate there's 1 electron in there. Electron configurations are a place where we do write the number 1. So 1s1. An orbital diagram is a little more of a picture. So here's a box. The box represents the 1s subshell, and we indicate the electrons as arrows. So it's a half-headed arrow, and so there's 1 arrow in that box. The direction of the arrow in the box represents spin. It's a fundamental property of electrons. And for our purposes, think of spin as like with a top, a spinning top, or a Beyblade, if you ever did those. So Beyblades can have a clockwise rotation or a counterclockwise rotation. You can spin in one direction or the other direction. Electrons have spin, and it's in one direction or the other. We represent it as arrows, 1 up or 1 down. The Pauli exclusion principle says that the orbital can hold no more than 2 electrons, and those electrons have to have opposite spins. So we symbolize those as 2 arrows pointing in opposite directions. So if we want to draw orbital diagrams for helium and for lithium. How many electrons does a helium atom have? 2. So it has 2 electrons. So we're always going to put our electrons in the lowest energy subshells possible. So the first shell has 1 subshell, it's the S subshell. And so we can put 2 electrons in this box. We'll put one with the arrow up and one with the arrow down. Yes?
So does it matter how we draw the arrows?
By convention, we always put the up arrow first and then the down arrow.
I meant like, hey, like
Half arrow? I don't think that really matters. Traditionally, we use a half-headed arrow, but I don't exactly know why. So lithium has 3 electrons. So here's that first shell, and it's 1 subshell S, and we can put 2 electrons in there. But the 3rd electron isn't going to fit. So we have to go to the next shell. Well, first we have to go to 2. So the next shell is 2, n equals 2, and that's going to have an S subshell. Every shell has an S subshell, and so we can put 1 electron in there. So those are orbital diagrams. You need to know the difference between an orbital diagram and an electron configuration. Orbital diagram is the one that looks more like a picture, the boxes and the arrows. The electron configuration is more of a shorthand. So I prefer to do the diagrams first because I think they make more sense. The electron configuration, I'm going to look at this and I'm going to use this shorthand notation to indicate how many electrons are in each of these boxes. So here I have the 1s subshell. So a 1s, and there are 2 electrons in there, so that's 1s2. Saying there are 2 electrons in the 1s subshell. Well, down here I have the 1s with 2 electrons, and I have the 2s with 1 electron. So this is 1s2, 2s1. I know it seems like gibberish at this point. I feel silly even saying it out loud. 1s2, 2s1. That's just like, what the heck? Anybody have any questions that they can actually put into words? I'm sure you're like, what the heck? Yeah.
So if you had something like boron, you would have 1s, 2s2, and then like 2p1?
Yes.
Okay.
Yeah. Just to make things more complicated, and really probably a big reason why the Bohr model didn't work, in a multi-electron atom, which is everything but hydrogen, the subshells within a principal shell do not have the same energy because of interactions between the electrons. So we would expect that the S subshell and the P subshell in the second shell would have the same energy, but these are actually a little higher in energy. And on the third shell, 3s and 3p are not exactly the same in energy. The p is higher. And then there's also the d subshell on the third shell, and that's even higher in energy. But it's higher in energy than the 4. And so they get all kind of wonky like this. Don't worry about that too much just yet. But let's look at carbon. So if we go back here, we can use this diagram to help us with carbon. How many electrons does carbon have? 6. So one way to do these is to just use this diagram and start sticking electrons in. So I can put 1 here and another one. That's 2 and 3 and 4. And then the next electron has to go to the next level, the next higher level, which is P. So there's 3 different orbitals here. Each orbital can hold 2 electrons. Yes?
So you would fill 4s before you went to 3d?
Yeah, 4s will fill before 3d. I know that doesn't seem right. So here I've got 5 electrons, and now the next electron, he has a choice. He could pair up with this one, or he could take his own orbital. What would you do? Really? Okay, you're on a bus, and there's 3 seats on the bus, and you can sit by this stranger, or you can have your own seat. It's going to take its own seat. So if we go to this, write the electron configuration in the orbital diagram. We've got 6 electrons for carbon. So we've got the 1s, and we can put 2 electrons in there. And then we've got the 2s, and we can put 2 electrons in there. And then for orbital diagrams, we represent the p orbitals as 3 boxes together, because there are 3 orbitals here in this subshell, but they all have the same energy. And that's 2p. And so when we stick the electrons in there, they're going to fill them one at a time first. And that's what Hund's rule tells us. When filling orbitals of equal energy, electrons fill them singly first with parallel spins.
So once it's filled up, then you can add it to another seam.
Yeah. So the next electron would go here, and then after that, they would start pairing up. Okay, so all of that probably was just really strange. Is that really strange? Yeah, okay. So here's the analogy that I have come up with. This is my best attempt to relate all of that strangeness to something we've experienced in real life. So the Quantum Hotel, a discount resort for electrons, in this case, Chemistryland. Okay, so all of those things we've been talking about, I can relate those to aspects of a hotel. So the principal shells, 1, 2, 3, 4, those are the floors of the hotel. Okay? The subshells within each shell are rooms. So the first floor has 1 room, the second floor has 2 rooms, the third floor has 3 rooms, the fourth floor has 4 rooms. The fourth principal shell has 4 subshells. On this first floor, these rooms are given letter names. So there's the S room. On the second floor, there's 2 rooms, the S room and the P room. Third floor, S, P, and D. And these are different types of rooms. The S room has 1 bed in it. P rooms have 3 beds in them. D rooms have 5 beds. F rooms have 7 beds. Weird hotel, 7 beds in 1 room. And there's a very strongly enforced rule, only 2 people per bed, and you have to have opposite spins. People don't have spin. Okay, so this is how I think about it. I think of electrons as being masculine, maybe because of my son Andrew, I'm not sure. So here's how we represent the orbital, right? The orbital is a bed in the hotel, and the electrons are people. So the electrons are guys, they come in, you're not allowed to sleep on the floor. So here's the first, see this is the head of the bed, and this is the foot of the bed down here. So the first guy gets in, and he's going to sleep right side up in the bed, because that's how normal people sleep in a bed, right? The next guy comes in, and he's like, I have to share a bed with this guy I don't know. Guys don't like that, do they? You agree with me, guys? That would be really, really awkward, like seriously awkward. So instead of sleeping right next to this guy, and he might get the wrong idea, you're going to sleep upside down. And you're probably sleeping way over the edge. You're upside down. It's like, there's no funny business going on here. I'm not trying to do anything, right? So it sleeps upside down. Okay, so that's what I mean about this. 2 people per bed, and they're going to sleep head to toe like that. Weird, yes, but at least it's something you can imagine, rather than electrons spinning, right? Okay, so the electrons are people and energy is related to money. So as you go higher in this hotel, it costs more to stay in the room. Electrons are cheap. They're going to go for the cheapest room they can get into. So if we think about this now, this is a weirdly shaped, not very earthquake-friendly building. This would probably fall down because it's got this weird shape. Okay. Here's the first floor, one room. It's the S room. On the second floor, there's one room called the S room. It's got one bed in it. The P room has 3 beds. The D, no, never mind. Third floor, S room with 1 bed, P room with 3 beds, D room with 5 beds. On the 4th floor, S room, 1 bed, P room, 3 beds, D room, 5 beds. Okay? But there's a weird pricing scheme going on here. The 4S room is cheaper than the 3D room. Why? I have no idea. Maybe it's some Groupon deal or something. You know, they just price these things. So that's just how it is, and we deal with that in a hotel. We're like, oh, you charge more for this than that? Oh, what are you going to do about it? There's no understanding it. It is. So this is cheaper. So electrons are going to go into this room before they go to that room. Okay? So that's enough to make you dangerous. We got to get out of here. To be continued.